Bill, you gave us a great explanation of cryptography, and I want to actually dig into a specific reference point. So, what is the true meaning behind the Chinese claim that they've broken RSA encryption?
There were some Chinese researchers that published a somewhat exaggerated article, and certainly the press did no favors by taking the exaggerations and running with it. And what they said is, we've broken RSA. RSA is a public key algorithm. It was kind of one of the first, still good. By the way, still good. Don't run for the exits. Um, and what they did is they said, look, we're going to use a quantum computer. So a quantum computer is different from the one that's sitting on your desktop or you're holding in your hand in your phone. It basically uses some weird properties I guess you'd say, of matter, where um, there are relationships. I'm going to get this a little bit wrong. I apologize to the real experts in the audience, but um, atoms actually can interfere and sort of communicate with each other in the low level sort of quantum media of reality. They influence each other. And so folks figured out how to isolate individual things, they call them qubits, that can talk to each other effectively in this special, like, super cooled medium that is isolated from all external influences to run computations. It sounds like science fiction. It's not. But the trouble is that they're not very big yet. They're not. It's not possible physically. Like, our engineers have not figured out physically how to put a lot of these little qubits together and have them communicate with each other and not be affected by noise and have errors break into the system. So the state of the art in the industry right now is Google, about a month ago, announced that they have a 105 qubit computer, and these are general purpose qubits. So that we'll just talk about general purpose qubits. Other industry leaders are, running around 50 to let's say 50 to 100 qubits seems to be about the state of the art. You need more than that in order to break of the current size of the public key algorithms that we're using. What the Chinese researchers announced is that they had used a moderately sized quantum computer. I think it was about a 50 qubit computer to break about a 50 bit RSA composite. And what that means, a composite, so what RSA is based on is you take two large prime numbers. It's easy to pick prime numbers. You multiply them together and you get a composite. And that composite's the public thing. You tell people, hey, this is our composite. We're going to use this in this system. What is hard is figuring out what were the two prime numbers. This may not be obvious to the folks listening why that's hard, because they're thinking, if I give you the number 21, you're going to say 3 and 7. That's easy. That's 21. It's not so easy when you get up to sort of uncountably large numbers, which is the space that we actually work in. So for commercial RSA composites, they're 2048 bits. You need roughly 3 times more than that in qubits in order to run the algorithm that would let you factor the composite. So you'd need 5 to 10,000 qubits in a coherent working system that stays working long enough to run the algorithm. It's a thing called Shor's algorithm that's used for reversing this thing. And it works. But all the Chinese researchers did is they did it for a 50-bit prime composite, or a composite, which is 14 digits, which incidentally you can do with a conventional computer a lot easier. That's the takeaway. Is you could do it on a conventional computer easier than it was to do it on a quantum computer. And so what they really were showing was the theoretical confirmation that we can use a quantum computer to factor composites. We knew that anyway. So this was in no way a breakthrough, and in no way an indicator that we need, there's nothing's changed. We know that that's possible. But what the industry has to think about is the fact that those quantum computers are going to keep getting bigger. And at the point where they are 5,000 to 10,000 qubits, they're going to be able to start breaking our composites and reading our mail. So we have to start planning ahead Now, this is, I talked early on about offense and defense and cat and mouse. We have to start planning ahead for when those quantum computers are that big. It's actually worse than that because the adversaries are already planning ahead and they are recording our sensitive and classified communications and storing them. They can't read them now, but they might have a quantum computer that's big enough in the next, and experts are on the fence, or experts are, let's say there's a range of opinions. The opinions range from about 10 years to 30 years before there'll be a quantum computer big enough. Okay, that seems like a while away. However, if you're a government and you're storing classified information, sometimes you need to store securely for 50 years. And so they are already worrying about the fact that stuff that they're supposed to protect for 50 years might be exposed 40 years too early in the worst case scenario. So it's a real present issue that foresightful planners are starting to think about.